So this topic that is about line minimization, which is about to do minimization for a cost function, a revalued cost function. So this kind of minimization, that is a numerical method, one of the numerical methods after the gradient descent. So the problem is that we are going to have a function with some decision variable, for example, a vector of x. This vector of x, it could be a single variable. That is the first case we are going to talk about, and then later on we extend that into a number of decision variable. Now, assume that we have two decision variables right here. It means that we have x1 and x2. And now I'm going to draw that figure in a three-dimensional domain, that is x1, x2, and this is f. And then assume that we have a function, and we are going to do minimization. And now the thing is that this is the flow chart we are going to describe this line minimization algorithm. Randomly in the beginning, we are going to initialize a starting point and some other parameters. These parameters, that is some other control parameters. So we are going to have, say, a random point right here. So I just randomly pick a point. So, and then we are going to compute a search direction. That means which way we are going to go, and as well as, for example, we are going to choose this way, and then that is how long we go from this point to the next point. That is the step length, and then update the parameters. The parameters, that would be the decision variables right here we refer to. So this is the x0, and then we jump to this point x1, and then note that this one, that is this x, that is a vector x. This x1, x2, they are one of the components in x, and then this x0, x1, that is, I'm talking about, maybe I'm going to use the bracket instead of putting a subscript right here to avoid confusion with these two. Yeah, so this is x bracket 0, and then in the next iteration we jump to 1, and then we go to this point, check for convergence. You note that this is different from the gradient descent. We are going to stop, we are going to stop until the cost function begins to increase. That means this is a minimum seeking algorithm. We are going to start from a point, rolling down until we reach the local minimum, and then stop. Yeah. Okay, and now this is a single variable case. That means we are going to minimize this real valued function, and x, that is just a single variable. Yeah, so fx, that is a continuously differentiable function because we need to use the gradient information. We start from the Taylor series expansion. Okay, so that means we have a function f, and then so we know that if we are going to expand that function at the point xk, for example, we have a function something like that. We pick a point. I denote this point to be xk, and then all other point, it could be any value of x. So we have a point right here. So x minus x, this is x, this is xk. So we have x minus xk, that is the difference between these 2 points. So the whole function of fx, which can be written in this form, fxk, that is, this is fxk, that is the y value, plus the first derivative of f at the point xk. That means we need to find the derivative information right here, and then to find the difference, x minus xk, and then half of the second derivative of, that is f double prime, at this point xk, and the difference x minus xk square, and this hot, that is the high order term. That means we can extend this to infinite series, f triple prime, and then that is the df to the power 3 to what I mean, that is d3f dx3 and so on. So it contains in the high order term. But anyway, to develop the line minimization, we only consider f prime, f double prime. Okay, we ignore the high order term. So in that case, fx can be approximated by the first term, second term, and the third term, and we are going to do the derivative df dx, that is doing the df dx over this term and set it to 0. It is mainly because if we would like to find the local minimum, at the local minimum point, df dx, that is 0. Yeah. So if you're going to do df dx on the right hand side, that is this term, we will come up with this bit. Note that xk right here, that is a constant. So f at the point xk, this is constant. So when we do derivative on this term, it becomes 0. Yeah. So the only variable right here, that is x. Yeah. Anyway, once we obtain this function, we are going to rearrange this term, put all xk term on the right hand side and the x term on the left hand side. We will obtain an equation something like that. Instead of using x, I'm going to use xk minus xk plus 1. It is mainly because this would be the update rule. That means when we get to the first point, for example, this is x0, and then according to this information, we are able to jump to this is x1 and then x2 and so on. Yeah. So this is the update rule. So when we get back to this flowchart or the block diagram, that is the search direction as well as the step length that is given right here. If you are going to look at this update rule, it looks like something x plus 1 plus xk plus delta xk. This delta xk, that is minus f prime over f double prime. Yeah. So this, it also gives you the information about the step length. That means how far we jump from xk so that we become xk plus 1. Yeah. So this is a single variable case, and then so we are going to extend this idea into the multivariable case. That means minimize as real-valued function x, that is a vector of decision variable. We have x1, x2 up to xn. So we have n decision variables, and then now we are going to do exactly the same. So we are going to do the Taylor series expansion over f as well as at upon xk. Yeah. So in high dimension, we have similar structure, but the only difference is that in the second term, as well as all the difference between x minus xk becomes a vector. Yeah. So we will have this approximation plus the high order term. We are going to do the same thing. That is, will ignore this high order term and then set df dx to 0 in order to develop the update rule for x. Yeah. So take a look at this one. Gradient of f, that is exactly the same as the meaning of f prime in single variable case. Yeah. So we are finding the slope in this term, and this term we have h that is given by this definition. We call this is the Hansian matrix. So when we talk about h, and then so it is something like this: partial square f x partial x1 x1, and then so we have partial square f x partial x1 partial x2. That is each element in the ij position that is given in this matrix. Yeah, it forms the matrix of the Hansian matrix. So this is a vector, and then so this is a matrix, this is a vector. Yeah. Okay, so when you multiply them together, it becomes a scalar function. Yeah. Okay. Now move on to the next step. We move the high order term. Yeah. We move the high order term and focus only on these, the first three terms. The f of x can be approximated by these three terms, and then we are going to do the gradient of f because we are talking about the same thing in the single variable case. That means when we talk about the stationary point, it happens that the gradient equals 0. So after we do gradient f, set it to 0, yeah, because this term is constant, and then it will not appear in the second expression. After that, we are going to rearrange this update rule, yeah. Put all xk term on the right hand side, the only x term that is on the left hand side. So we replace that by xk plus 1 because we do the same thing. That is, we start from x0 and then after the update it becomes x1 and so on. So until we reach the local minimum. Yeah. So take a closer look at this one. If we are going to replace h inverse by hk in the gradient descent approach, and then this one is reduced to the gradient descent method. And one important thing, that is, when we do the update, we need to find the inverse of h if the dimension of x that is high or very large, and then it is very computational expensive. Yeah, so it depends on you whether you would like to use a constant hk like the gradient descent or the line minimization. Yeah, so now just to summarize a little bit about the advantages and disadvantages of the gradient descent and line minimization. Both of them, they are very robust and very with a quick convergence because we are looking for the local minimum and minimum seeking every time we are going to find a better solution, and the solution is tractable. That means computationally we are able to solve the solution iteration by iteration. The disadvantage, that is, it works with gradient. If f is not differentiable, for example, f prime does not exist, and then if we do not have f prime exists, and then we cannot apply this word. And also, it does not guarantee global minimum. If we have a multimodal function, many local minimum point, it is sensitive to the initial guess. Yeah, if we start from this point, we find this point. If we start from this point, we find the local minimum. That is right here. So we do not have any clue about whether the point find that is global minimum or not. And it does not work well with this quick variable. For example, if the decision variable x1, it only takes 1, 1.2, 1.5, this discrete variables, and then this method does not work. Yeah, so from the above we know that this method very easily the solution is trapped in the local minimum. So if we would like to find a better solution, maybe we are going to run it many times with different initial conditions, so that for example, this time we find this time with this initial condition we find that, this time we find this local minimum. So compare all of them, and then we are going to pick the best one. Yeah, okay.